Hi everybody, in this video we're going to talk about how astronomers measure the size of things and the distances between objects in the sky with angular measurements. We can't actually tell the physical distance between two objects or how big, say, the sun is just by looking at it in physical dimensions, but what we can do is actually see how large they appear to be, how much of the sky they span in an angular measurement. So this is going to be hopefully a little bit of review of angles. I know that it's been a while since a lot of you have played around with angles and those ideas. So bear with me. This does take a little bit of thinking, maybe outside the box a little bit, but hopefully you'll understand what angular measurement is after I go through this video. So I've tried to put together a little bit of a cartoon here, and I made a more full cartoon that I'm going to put on Canvas that is just a slideshow. I highly recommend using the PowerPoint version and presenter mode to go through that, or you can download the PDF. But I want to talk to you about angular size and angular separation. And why are we going to be using such a strange way of measuring things? Well, let's imagine that we have these two people right here. Here's my cartoon Galileo and a friend. She's just hanging out with Galileo that day, and they're trying to figure out how big the sun is. So if you go outside and you look at the sun, or you go outside and you look at the moon, they appear to be about the same size in the sky. We know they're not the same distances though. But whenever you look at them, you can't tell how physically far away they are or how physically large they are. You can't tell how many miles or kilometers they are away or how many kilometers they are in diameter. We cannot directly see the physical sizes and the separation distances. And whenever you go to the stars, you see two stars in the sky. You can't just look at them and sort of judge and go, I got one right there and one right there. That's definitely 7 light years. You just can't do that. What we can do is actually measure how much of the sky it spans. And we can remember that you have 360 degrees in one full circle. So we can imagine 360 degrees spinning all the way around and measure how many degrees something covers in the sky. That's what we can measure, the edge-to-edge size of things or the distance between two objects and how many degrees exist between them. And I want to actually help you understand these. So right here, Galileo and his friend, they're having a conversation, and he says, hey, do you know how big the sun is? A reply, I sure do. It's about the width of my finger held at or half the width of my finger held at arm's length. So what she's doing here is she's making an angular measurement. How much of the sky does the sun cover up? And it's about half the same size as the sky that her finger covers up held at arm's length. We just need to know how much sky that is measured in angles, and it's about half a degree. And of course, this is not the physical size. This is not the size of the sun in physical units. The sun isn't half a finger width in diameter. That's how big it appears to be from our vantage point. So really what she's doing right here is as she holds up her finger at arm's length, the one edge to the other edge spans about 1 degree of the sky. So that means that I'd have to hold up my finger and then move it over 1 finger width and move it over 1 finger width, move it over 1 finger width. And if I did that, I could spin all the way around the sky, all the way around from 1 finger width to the next, and it would be about 360 finger widths, so 360 degrees around. So she knows that if she holds up her finger at arm's length, that's about 1 degree of sky, holds it up against the sun. I do not recommend staring directly at the sun. In fact, just go beyond recommendations and say, do not stare at the sun with your naked eyes. You will cause permanent damage to your eyes. But if you could hold up or you could cover up the sun with your finger, and you would notice that it would span about half the width of your finger, your pointer finger at arm's length. That's about half a degree. So she has measured the angular size of the sun. The angular size of the sun is about half a degree in the sky. And now Galileo, being Galileo, he's like, oh, well, now I could use some geometry and I could use that angular size. If I knew how far away it was, I could connect how far away it is and how big it appears to be use some geometry to figure out how big it really is. And that's what the cartoon is about. It'll walk you through that exercise to reinforce some of this, and it was just a little bit fun to create. So in this scenario that I've drawn right here, the angular size of the sun would be 1/2 degree. And that's just how many degrees does it span from edge to edge on the sky. What you need is just some measurement, some tool where you can measure how many degrees things are, how many degrees are spanned on the sky, how many degrees are between one point and another point, which you could use a variety of tools to do that. And we've already discussed one of them. A very crude tool is using the fact that your finger at arm's length spans about 1 degree of sky. I highly encourage you to go ahead and spend some time citing some things around wherever you're watching this video at and measuring their angular sizes. And at the end of this video, I'm going to give you some more tools, some rough estimates of how big angular sizes are using your hand at arm's length. So here, we would say that the sun has an angular size of about 1/2 degree. We can do the same thing. And now let's say they're out at night and they see 2 stars, and you can't physically tell how far away they are from one another. It could be less than a light year. It could be 7 light years. It could be 50 light years. It could be 1,000 light years. That is the physical distance between these stars. You just see them as 2 points in the sky. You can measure the angle between them, how much angular sky there is between those 2 stars. Again, it'd be 360 degrees to spin all the way around the sky. So here we have Galileo, looks at this star, can measure 2.3 degrees between them. You can always use things like, if you remember, your protractors to measure your angles and things like that. So in this case, Galileo would measure 2.3 degrees between those 2 lines. And we would say that these stars have 2.3 degrees of angular separation. So again, we can't tell how physically far they are apart, but we can describe how far apart they are using angular separation. So hopefully this helps you a little bit with angular size. It's just how many degrees does something span across the sky, whether that's a distance, that'd be an angular separation, a distance between 2 objects, or if you're saying measuring the sun from edge to edge, the angular size of an object. Unfortunately, however, degrees are tragically too large for astronomy. For us to do anything meaningful in astronomy, we need to accurately measure these angles on the sky with usually a precision of about 1/10,000th of a degree minimum. Usually much more precise than that, 1/100,000th or more of a degree. So that's a very small angle on the sky. Obviously, we can't use degrees for that measurement. So what we want to do is we want to use some smaller unit than degree. And astronomers have a special set of angular measurements, for things that are smaller than 1 degree. And these 2 different angular measurements that astronomers use are formally called minutes of arc and seconds of arc. We shorten minutes of arc to what we just call the unit, the arc minute, which is usually just written as arc min. And then the seconds of arc, we usually just call those arc seconds, and it's usually just abbreviated arc sec. All right, so what is an arc minute and an arc second? We know that they're going to be smaller than a degree. So here we have a circle. We know there are 360 degrees in a circle. Let's just take one of those degrees. So like what would be between, I guess it's kind of hard to see without a white background here. What would be between 90 and 91 right there? That would be 1 degree. And let's break that 1 degree into 60 smaller equally sized units. So we'll take 1 degree and break it into 60 sub-units, equally spaced between one another. One of those would be an arc minute. So there are 60 arc minutes in 1 degree. So we take 1 degree, we break it into 60 equally sized smaller units. We call each one of those 1 arc minute. So 1/60th of a degree. An arc minute is a 60th of a degree. Pretty small, right? But not near 1/10,000th of a degree. So we need to go smaller. Now let's take 1 arc minute and break that up into 60 equal parts. Because there are 60 seconds in 1 minute, we will call taking 1 arc minute and breaking into 60 smaller subunits. Each one of those subunits we will call 1 arc second. So there are 60 arc seconds in 1 arc minute. And since there are 60 arc minutes in 1 degree, that means we would have 60 times 60, 3,600 arc seconds in 1 degree. So 1 arc second is 1/3600th of a degree, which puts us right about where we need to be doing meaningful astronomy. The arc second, even though it's a ridiculously small angle, is a large angle in astronomy, or at least whenever we're trying to measure things precisely. Now, I know these are new units. These are things that I highly recommend just writing them down several times, just to first learn what the definitions are, that there are 60 arc minutes in 1 degree, and that there are 60 arc seconds in 1 arc minute, and start associating those in your brain, because just getting those sort of rote memory will really help you as we move forward, because we're going to be saying arc minute and arc second all the time in this class moving forward. And I just want to give you another graphic so you can see here just what I was trying to show you by holding up a protractor. Here's a graphic of a protractor. So if we want to measure where this is very, very precisely, we could go ahead and would measure about 60 degrees. We'd take between 60 and 61. We'd break it into 60 arc minutes. And then we might see that the angle we're trying to measure lies right here. So we would take this 1 arc minute between 35 and 36, break that into 60 arc seconds, and then we could count off how many arc seconds. So the very, very, very precise location of this red line would be at 60 degrees, 35 arc minutes, 18 arc seconds. You could turn that into decimal degrees if you wanted to, but this shows you that in 1 degree you have 60 arc minutes, and in 1 arc minute you have 60 arc seconds. And I said I'd end this video by giving you something so you can go ahead and measure the angular sizes of things around you. I'm going to do that here in front of you. I'm going to measure the angular size of that globe sitting up there, but I want to do that full screen. So I'll do that after I introduce all of these to you. So if you hold out your arm, your fist at arm's length, so all of these are angular measurements for how big your fist or parts of your hand appear at arm's length. If you hold up your pinky finger from one side to the other, that's about 1 degree. So holding up the finger I was earlier is a little bit bigger than a degree. Holding up your pinky finger, which is hard to do and feels weird, is closer to 1 degree, which is why I usually just use my pointer finger. It's easier for me to hold that up. It's a little bit bigger than 1 degree. 3 fingers, so if you're going to pay some respects to Hunger Games, 3 fingers side to side is about 5 degrees. My favorite one, a fist from this edge to this edge, held at arm's length, is about 10 degrees on the sky. If you're going to a rock show, the distance between your 2 fingers measures about 15 degrees of angular separation on the sky. And if you're going to go surfing, you're going to hang 10. You should really say you're going to hang 25 degrees, because the distance between my thumb and my pinky finger is about 25 degrees. So that gives you a whole suite of ways of measuring angular size without having to bring really, really precise instruments or having specialized equipment. A good way to do a estimation. My favorite is the fist at arm's length, because 10 degrees, and the sun doesn't just travel vertically or horizontally, it travels at an angle. And it moves about 15 degrees it moves 15 degrees per hour, because it goes around once every 24 hours, and 360 degrees in one circle divided by 24 hours moves 15 degrees per hour. But on average, vertically, it moves about 10 degrees per hour. So if I want to estimate what time it is, I can always go outside, find where the sun is, count how many fists above it is the horizon. If it was 3 fists above the horizon and the sun is setting, then the sun would set in about 3 hours. Just a very useful thing. And to give you an idea of how small an arc second is, If you took a penny and went for a little hike 2.5 miles away and prop that penny up so you could see it from edge to edge, hike back so to where you started, you looked at that penny from 2.5 miles away, the amount of sky that it would span, the edge to edge angular size of that penny would be about 1 arc second. So a really, 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 really small angular size. Okay, so now let's do one practical example before I end this video. So you can see that I have this globe up here, and I'm gonna try to move the camera so it's a little bit closer to where I am. So it'll be about the same, and let's see if I can line things up. So I would like to know what the angular size of that globe is measured from where I am sitting. So what is the angular size of that globe for how far away it is from me? So I can hold up my fist, and if I put it over there, it covers about 1 fist. I'll check with my personally. Yeah, it's a little bit bigger than, or a little bit smaller than 1 fist. So it would be about 8 degrees, somewhere around 10 degrees of angular size. And you can do that for other objects if I want to know what the angular separation is from this side of this lamp to the other side of the lamp. Maybe now, this time, I would want to use, say, my pinky finger and hold it up at about arm's length. So it'd be 1, 2, 3, 4, 5. That should be about the same as the 3 fingers. Yeah, about 5 degrees in angular size. All right, so you've seen a couple of practical examples. I really encourage you to pick some objects that are around you and try to measure the angular size of them. Pick 2 different objects, try to measure the angular separation between them. And that will start giving you a sense of what we mean when we say angular size and angular separation, which are very common things that we say in this class. So the faster you can become familiar with them, the better. All right, thanks for tuning in.